Okay, next hint is that they are independent, so you can write the posterior the likelihood as a product of the individual probabilities of getting individual values of xi. How many of you have introduced an angle? Yeah. So it's convenient to change variables to the angle. Okay, so the advantage of changing variables to the angle is that we want to calculate the probability of xi's, but that's slightly complicated, but what we do know is the distribution of the angles psi I. So if we transform from one to the other, then we can get the distribution of probability distribution for the xi. So what's the distribution of psi I? It's uniform, yeah. If in degrees, yeah, fine. Or one might argue that for those, yeah, 1 over 2 pi, or in fact, because we're only interested in the ones that hit the shore, then for the ones that hit the shore, then the range of psi is actually only from minus pi by 2 to pi by 2. So P of psi normalizing it, that's not very important, it's 1 over pi, but uniform. Okay, so if we want to, if we know the distribution of size, then we can get the distribution of x's, xi's, just using the conservation of probability. So this thing is in fact not dependent on x0 and y0. So it's just 1 over pi within that within this range. So we need to calculate this, you need to calculate what that derivative is. Is anybody close to a solution? Do you want a bit longer to try it, or shall I? A little bit longer. I don't know how big the prize is. You got a result. Okay. So can you write down Can you write down this? Two minutes left. So next hint, if you haven't got that. If you differentiate town, you get set square. You have? Okay, write it up. Right, big. The competition is still open. That might be right, but we need to check because there's too much trigonometry still in there. In other terms, yeah. I'm not saying that's wrong, but we need to check afterwards. Anybody else got a solution that has no trigonometry in it? I'm not giving you the solution yet. I have a slightly longer. One more minute. Okay, we'll check with you whether your answer is correct, but so in order to get the P of x, I, we take this, which is uniform, so we know what this is, we need to calculate this. So given the relationship between psi and x, we can differentiate sec squared psi dx, psi by dx is 1 over y naught, differentiating this. And sec squared is 1 plus tan squared, so that's 1 plus xi minus x naught over y all squared times d psi by dx 1 over y. Okay, so that tells us what this thing is. That's what we need to do the transformation. So we can then write down what p of xi is. It's just a constant times this object, which is 1 over y naught divided by the square bracket. So that. Okay, so it's actually a product of Cauchy distributions. So these distributions, these weird probability distributions can arise in real physical situations. So if you only have one measurement, then basically you'd have a distribution of the x position for a given y. The distribution of the x position would be a Cauchy distribution. So you would know very little about where it was. The variance on your of this distribution is infinite. But as you add in more, then this becomes well behaved. I think we probably just need two observations and it becomes quite well behaved. This is some of Steve Bell's own numerical investigations showing what happens as you increase the number of flashes that you get, and the more that you get, and the smaller the posterior range is. So you tie down the positions of the satellite, of the lighthouse. Okay, so there's a little bit of geometry involved with that, but hopefully you have seen how you can just use a Bayesian method to give you the posterior. Let me go through the frequentist way to do this. So what a frequentist analysis would do would be to define an estimator for the quantities that we're looking for. So an estimator for x0 and an estimator for y0. So let's forget about y0 and just think about an estimator for x0. So what we have is some set of random values that's come from a lighthouse offshore. So what would be your idea for an estimator for the x position of the lighthouse? What would you do? The mean, yeah, okay. So you just take the average. I think that's the only sensible thing that you could do. We know that the distribution of the light is symmetric, so the average would be sensible. Okay. So let's do that. Let's investigate what happens. It's quite interesting. So let's, just so that we tie in with what we did with the central limit theorem, let me write the average as x0 hat. So that's 1 over n times the sum of the x positions. So let me write that as n times x. So x is just the sum of the positions. Now we know what the characteristic function of a sum is. It's just the nth power of the characteristic function of the individual variables. So let's work out the characteristic function for a Cauchy distribution, because that's what we have. So this doesn't have the 1 over pi y0, so let's go back just to see. So for the probability distribution for an individual observation is what's in this product here. So it's this Cauchy distribution. It's a Cauchy distribution, but there's a 1 over pi y0 there, which I will just not be there for a moment. We'll need to put it in later. So this is the Fourier transform of the Cauchy-like term, and the value of that, if you evaluate that, is e to the I k x0 minus the modulus of k times y0. If it's mathematical or something. So that's the individual characteristic function apart from the normalizing 1 over pi y0. So we can then just write down what the characteristic function for the sum is, because we just take this and raise it to the power n. So that is equivalent to multiplying the exponent by n. So I'll just put some n factors of n here in the exponent. So that's the characteristic function of the sum of the xi's. So in order to get the probability distribution for that estimator, then we need to invert the transform, invert the characteristic function. And we can do that because the form of this is actually exactly the same as here, except that if you replace the x0 here by n times x0, then you have the same function. And if you replace y0 by n times y0, then it's the same function. So if you make those substitutions, then you end up with exactly the same thing on this side. So I can just trivially invert the transform simply by writing down the probability distribution, but with x naught being replaced by n times x naught and y naught being replaced by n times y naught. Okay, so that will do the inverse of the transform. And I've reintroduced the 1 over pi y naught here, which becomes, when you do the inverse transform, it becomes 1 over pi times n y naught. So that's the probability distribution, not for the average of the variables, but it's the probability distribution for the sum. So that's probability distribution of n times our estimator of x naught. We can just change variables using the conservation of probability to get the probability distribution for x naught hat. It just introduces a factor of n, so that's easy, this n disappears. So you end up with the probability distribution for the estimator, and it's given by this. Which is quite interesting, because it's actually exactly the same as the distribution of any individual xi. So it means that if you, however many observations you make, if you average them, you end up with a distribution which is no narrower than you would have if you just had a single flash. Okay, so this looks like a violation of the central limit theorem, but in fact it's not. This is one of those cases, one of those pathological probability distributions that gets no narrower as you average more and more things. So of course, Steve likes and I like this example. It's just a beautiful example where the Bayesian gives you a very nice answer, and if you do a frequentist calculation, it's completely hopeless. Oops. Maybe it is what I wanted to say instead. Yeah. Okay, so are there any questions on any of that? Yeah.
You said that when we are in a Bayesian statistic methods, we get more data or results or errors over them, right? But when you say more data, that's really, I don't know, general. So how do I know how much data should I get to get
Okay, that's an interesting question. So there is one thing which we will cover tomorrow, which is how you can forecast how big your errors are going to be using a technique called Fisher matrices. So there is a way that you can get an estimate of how big the errors are going to be before you do an experiment. So it can tell you, in this case, if you wanted to, you could work out how many flashes you would need in order to constrain the position of the light output to whatever precision you want. So there are ways to do it, and we'll cover those tomorrow. Anything else? Okay, if not, I'm going to hand back to Leacher, who's going to...
Oh, it's me.
Is that right?
Alma, ¿quieres que haga yo? Creo que ellos acabaron ya, ¿no?
Well,
Ella acabó. Ella acabó como con 50 minutos antes. Falta que había... O yo no hablo. ¿Sí?